I told you guys we were going to have a speaker. This is Mr. Metzler. I've been bragging that you're the top end group and you're going to have some good questions for him, so don't let me down. Okay? We're going to, the presentation he has will go right to the bell. So I want to get started right away here. He's going to tell you a little bit about his background. But what we're going to be looking at here is kind of the evolution of the different classes of aircraft carrier, and I think through the presentation you'll understand why this is kind of a thing that he's doing, because he spent a lot of time working on it. So, all yours.
As he said, my name is Timothy Metzler. I used to be a special agent with the Naval Criminal Investigative Service. I was a civilian employee. I was not active duty, so I was outside the chain of command, which is a good thing because I have had commanding officers try and order me around. And I would tell them, look, I'm not in the military. If you want it changed, talk to the Secretary of the Navy. We'll talk to the Director NCIS, and they'll give me direction. So I could not be influenced by anybody in a uniform, which is a good thing because commanding officers don't want things reported because it could hurt their careers. Here's just a quick summary of my assignments. So 02 I started, so 02 and 03 I was in Virginia at the Norfolk Naval Station and the Portsmouth Naval Medical Center, assigned to do general crimes. So anything from stolen license plate to deaths, homicides, that kind of stuff, and everything in between. 2003 I deployed with the Marine Corps as a civilian. I was the OIC of a personal security detachment for the commanding general, so our job was to protect him at all times. When I returned in 04 to Norfolk, I was assigned to the field office's counterintelligence squad. And when I got there, they told me, we want you to work on the CBN 21 acquisition program research. And I said, okay, I have no idea what that is, but I'll figure it out. So CBN 21 was the research effort to figure out what the next generation of aircraft carrier should include as far as technology, capabilities, all that good stuff. Newport News is the shipyard that builds aircraft carriers for the United States Navy. So that's where everything is being done. So that's where I was for 6 years. And just so you guys understand, CBN is an acronym. It means a nuclear-powered aircraft carrier. So C is carrier, B equals aircraft, heavier than air, and N means nuclear, right? So this is tradition right here. This, right, we don't have lighter than air aircraft anymore, but this came about when we did, so that's why it's CBN, right? It's just the way the Navy does stuff. Once they come up with something like that, they're never going to change it to more modern stuff. So after 6 years of working on the protecting the technology of the next generation of aircraft, the Navy moved me up here to the Knowles Atomic Power Laboratory, where I did counterintelligence work for another 2 years, solely for naval reactors, nuclear reactors. That's all I focused on. And just to put in perspective what I was protecting, there was me here, one guy in Pittsburgh, and one guy in DC. So between the three of us, we were protecting 65 years of research that cost the U.S. taxpayer about $65 billion. So that's what we did, make sure that that information was not compromised. This is a picture of the Newport News shipyard. The waterfront is 2.5 miles long. It's a rather large shipyard. And on any given day, there's about 35,000 people here. So 20,000 work for the shipyard, about 5,000 contractors for the shipyard, and up to 10,000 sailors could be here a day, depending upon how many ships there are at the shipyard. So this is where I would go every day to talk to people, anywhere from the president of the company down to somebody applying for a job. This right here is an aircraft carrier under construction in a dry dock, right? So they build them in pieces in this building, and then they take the pieces and put them together in the dry dock. And it could take 5-6 years to build one of these things. So before we go any further, I just want to talk a little bit about how carriers go to war. So a carrier is part of a carrier strike group. An aircraft carrier is just a ship. There normally are not planes on it. But when it goes out to sea, as a strike group, they have these aircraft along the bottom here assigned to the carriers. So 4 fighter squadrons 11 fighters each, so they use FA-18s and F-35C Lightnings. Those are the main combatants. There'll be one squadron of electronic warfare planes, 6 planes. They go up and jam enemy radars and communications, that kind of stuff. Then we'll have a squadron of airborne radars, right? So they are higher up. They can see more of what's going on than the ship on the surface. And all these planes and ships are interconnected electronically, so they'll beam their information to others. We'll have 2 helicopter squadrons on the aircraft carrier. One is a general purpose squadron, and one does like anti-mining ops and anti-submarine warfare. And then lastly, there'll be a squadron of 2 cargo planes that just fly from the carrier to shore to pick up people, parts, whatever's needed, and bring it back to the ship. That's all they do. It's basically like a truck driver in a plane. Oops. Ship's company of personnel, so a Nimitz-class aircraft carrier has about 3,000 sailors just to run the ship. And then when the air wing comes aboard, the air wing will bring about 1,500 people, that's pilots and maintainers and support staff. And then when the carrier strike group admiral's on board, the guy in charge of all of this, it'll be an admiral, and he or she will have about 500 people that work just for him or her, right? That's their command staff. So when the aircraft carrier is out to sea as part of a strike group, you're looking at about 5,000 people on the ship. In addition to the aircraft carrier, we've got other vessels that go with it. Upper left-hand corner is a guided missile cruiser. There'll be one of those, and then 4 to 6 guided missile destroyers. Those surface ships do anti-air, anti-missile, anti-surface, and anti-submarine warfare, and they're located, maybe hundreds of miles out from the aircraft carrier to prevent any bad guys from getting close to the aircraft carrier. The guided missile destroyers will do most of the fighting. The guided missile cruiser is really the quarterback of the team. He's calling the plays for everybody else. We'll also have 1 or more attack submarines in the mix. They could be close to the carrier or they could be 1,000 miles away. They kind of do their own thing. And then we'll have at least 1 support ship. This will go back and forth between the strike group and land and pick up fuel, food, ammunition, spare parts, people, whatever, and bring it out to the ships. They refuel at sea, right? It's called an underway replenishment. 2 ships 300 feet apart, going the same speed, and they just transfer stuff back and forth. So when a carrier strike group is out to sea, they can control up to about a 500 mile diameter circle. So the red circle on the screen is 500 miles. That's the size of the battle space that they'll be aware of and control, right? So you can see how big that is compared to the United States. They're scaled the same. So there should be nothing in that red circle in the air, on the surface, or under the water that the Navy doesn't know about. They should be able to detect anything in that zone, and if need be, destroy it. So now we're going to just talk, before we keep going on, about modern aircraft carriers. We're going to try some history. So over 100 years of history in 25 minutes. And if you guys have any questions as we're going along, just shout them out.
On November 14, 1910, the U.S. Navy successfully launched an airplane from a light cruiser USS Birmingham. 2 months later, the first arrested landing occurred on board USS Pennsylvania. These 2 events were considered the starting point of American naval aviation. But a true game changer came 12 years later when a 7-year-old collier, USS Jupiter, was converted to an aircraft carrier and renamed USS Langley. With a 542 feet long flight deck and retractable masts and exhaust pipes, USS Langley had a flush deck design. USS Langley was an experimental ship, so it was not restricted by naval treaties. Its goal was to figure out a basic doctrine on how to operate an aircraft carrier. As the first landings and takeoffs occurred, the U.S. Navy gained invaluable experience in the flight deck of USS Langley. As experimentation continued, arresting wires and catapults were tested, modified, and improved. Let's not forget that in this process, many airplanes crashed, flipped and nosedived. Pilots were injured, there were even a few fatalities. But they were determined and eventually they got it. They figured it all out, even though at a great cost. The earlier arresting systems were weight-based, with the initial system relying on sandbags. The wires were suspended about 10 inches above the deck, and this worked, but was by no means perfect, as it would result in what was called instrument phase. The instrument phase was a distinguished mark of Langley pilots, as they spent 5 years figuring out the basic operations on the carrier, and oftentimes during unsuccessful landings, the pilot's face would smash against the instrument panel, wiping out teeth and breaking noses. It was rough. The weight-based system was in use until the 1930s. After that, it was replaced by hydraulic cylinder-type arresting gear, which allowed for landing of heavier aircraft at higher speeds. USS Lexington and USS Saratoga were the first two American carriers to feature islands. The biggest benefit of the island was redirecting exhaust plumes up and away from the flight deck. The biggest downsides were increased air turbulence and decreased clearance on the flight deck. The island superstructure was a great hazard to landing aircraft, but its benefits outweighed the risks. The islands on both carriers were installed on the starboard side of the carrier. This was intentionally done because propeller planes would inherently swing to the port side due to the torque effect of the propeller spinning clockwise. Pilots had to correct for this during takeoff and landing, and thus it made sense to have the island on the starboard side. Another benefit was that it was easier for the aircraft carrier to navigate in smaller channels. Lexington-class carriers were originally laid down as battle cruisers after World War I. However, during construction, they were modified to be aircraft carriers. Lexington and Saratoga proved extremely successful as aircraft carriers, and they convinced the U.S. Navy of the value of large carriers. Lexington-class carriers were almost 900 feet long, had a top speed of up to 35 knots, and carried about 90 aircraft. They had 2 elevators and a giant hangar divided by a fire curtain. The height of the hangar was not exceeded until mid-1950s. Lexington and Saratoga were the largest aircraft carriers in the U.S. Navy until 1945. During peacetime between World War I and World War II, Lexington, Saratoga, and Langley often engaged in wargame exercises. This is when many strategies on how to best utilize aircraft carriers were developed. Carriers, battleships, and other surface combatants were split into 2 teams and were presented with various problems to solve. Fleet Problem 10 involved testing shore and naval defenses of Panama Canal against a battleship attack. In a daring move, USS Saratoga separated from the fleet with a single escort cruiser to make a wide sweep to the south and attack the Panama Canal. The airplanes were launched at 2 o'clock in the morning while being 200 miles at sea. At dawn, the Panama locks were hit with a dive bombing attack. The defenders were taken completely by surprise. The effectiveness of this attack was the beginning of Carrier-Centered Task Force, as was advocated a year later by Lieutenant Commander Forrest Sherman. In the early days of aircraft carriers, if the airplane failed to catch the arresting wire, it was improbable that it would take off again. For this reason, barrier wires were installed to prevent aircraft from crashing into the crew and other airplanes that were parked in front of the landing area. Crashing into the barrier wires would usually result in damage to the airplane and injuries to the pilot, but it was much better than the alternatives. If an airplane landed successfully, the barrier wires, which were installed 3 to 4 feet above the flight deck, would be lowered so the airplane could taxi over them. In 1931, USS Ranger was laid down. This was the first American ship to be designed and built from the ground up as an aircraft carrier. During the design phase, Ranger was conceived to have a flush deck design, just like the Langley, but during construction, an island superstructure was added. Due to the Washington Naval Treaty, Ranger was a relatively small carrier, having a displacement of about 14,000 tons. While the vessel was still under construction, the U.S. Navy realized that the minimum effective size of a carrier was at least 20,000 tons. So in a way, Ranger was obsolete even before its construction was completed. Due to budget cuts as a result of the Great Depression, a lot of design features were removed from the carrier, such as extra elevators, elimination of catapults, simplified fire control, and so on. But it did still feature weapon elevators. and it appears to be the first carrier to ever have them. USS Ranger was kind of a flop, considering it was built from the ground up as an aircraft carrier. She was deemed too slow to operate in the Pacific, so she missed most of the action during World War II. Instead, she was deployed in the Atlantic and after the war was sold for scrap. Yorktown class and Wasp class were the last carriers limited by the Washington Treaty. There were 3 ships in the Yorktown class, including USS Enterprise and USS Hornet. USS Wasp was the sole ship of her class. Yorktown-class carriers had been given an extra elevator since the existing 2 elevators on the Lexington-class were proven to be inadequate. Deck edge elevators were first introduced on USS Wasp as an experiment and were later incorporated into the Essex-class carriers. If the legacy elevator ever broke and got stuck in the down position, that would affect flight deck operations, but having an elevator on the side would not compromise the carrier's operations. Deck edge elevators would become the norm in the future carrier designs. Another benefit of this design was increased deck space when the elevator was in the up position, as it provided additional parking space. Essex-class carriers were the most numerous class of capital ships built in the 20th century. In total, 24 ships were built out of the 32 that were ordered during World War II. Since the class was not limited by naval treaties, it was about 60 feet longer and 10 feet wider than the previous Yorktown class. As the airplanes kept getting larger and heavier, a lot of attention was directed towards the larger size of the flight deck and the hangar space below. Other innovations of the Essex class included torpedo protection, hangar deck armor, and the bulbous bow. Early flight decks were made of wood and no armor. This made the flight deck lighter, which lowered the ship's center of gravity. The wood was also easy to repair. The issue was that bombs could easily penetrate the flight deck and reach both the hangar deck and even lower decks. Pre-World War II, carriers such as Yorktown and Wasp class had little to no armor. This was a severe design flaw, which was even acknowledged during the construction phase, but nothing could be done, because the carriers had a restricted tonnage limit due to the treaty. The absence of armor on USS Wasp proved fatal when she was lost due to a torpedo attack in 1942. Similarly, USS Yorktown was lost during the Battle of Midway, and USS Hornet was lost during the Battle of Santa Cruz Islands. Meanwhile, none of the Essex-class carriers were lost during World War II, as these ships were much more heavily armored. Specifically, a 2.5-inch hangar deck armor was introduced on the Essex class. These carriers did take a lot of beating from bombs, suicide planes, and fires, but none were lost. USS Franklin was the most heavily damaged carrier during World War II that still survived. She was badly damaged by a Japanese air attack in March of 1945, but still managed to return home on her own power. Similarly, USS Bunker Hill was severely damaged by 2 kamikazes within a 30-second period. She also survived and made it back to Pearl Harbor. From the lessons learned during World War II, a decision was made to start adding armor to flight decks. The Midway class of 3 carriers received a 3.5-inch armor plating at the deck level and 2-inch plating at the hangar level. Midway was the first class of American aircraft carriers which had armor protection for hangars. Of course, the downside of adding all this armor was increased top heaviness of the vessel, which resulted in poor seaworthiness, as the flight deck would get washed over during higher sea states. The Midway-class carriers were capable of embarking as many as 137 aircraft, but it was deemed impossible to operate more than 120 from a single carrier. Midway-class carriers, in their original configuration, were the last ships to be limited by the Panama Canal Locks limit size. By the end of World War II, it became clear that the future of naval aviation was in jets. But this meant that carriers needed to be modified in order to accommodate these heavier and faster jet aircraft. The modifications varied from simpler things like adding a jet engine test facility at the fantail area of the carrier to major modifications like a complete redesign of the flight deck. The angled deck was first tested in 1952 by the British and later by Americans on USS Antietam, which was a modified Essex-class carrier. Antietam's flight deck angled 10.5 degrees to the left of the longitudinal axis. jet aircraft's higher speed would have required the entire length of the centerline flight deck to arrest the airplane on landing, which would have meant no aircraft could take off if one was landing. Obviously very inefficient. But an angled flight deck allowed for simultaneous launch and recovery operations of aircraft. But even more importantly, the new design fixed another big issue, because now airplanes that failed to catch an arrestor cable could accelerate and relaunch without any risk to the parked aircraft in the front. The trials on USS Antietam were so successful that the US Navy decided to retrofit angled flight decks onto most of the Essex and Midway class. The Forrestal class of 4 ships was the first class of supercarriers. Forrestals were about 25% larger than their predecessor Midway class. Specifically, they were 100 feet longer and nearly 20 feet wider. Additionally, a deeper hull resulted in much better seakeeping than the previous class while still incorporating an armored flight deck. Originally, Forrestal and Saratoga were laid down as axial deck carriers, but during construction, both were converted to angled deck ships. This allowed for a larger island, roomier hangars, and better damage control. Forrestal class also had 4 catapults and 4 elevators, compared to just 3 of each on the Midway class. As the first supercarrier, Forrestal's design was not mature, so some mistakes were made. In particular, the positioning of the portside elevator was problematic to say the least, as it was located at the fore of an angled deck next to the catapults, and this severely limited flight operations whenever the elevator was in the down position. This issue and other ones were fixed in the future Kitty Hawk class carriers as the elevator was moved to the aft end of the angled deck. Kitty Hawks were essentially Forrestals with a few improvements, like the angled deck being 40 feet longer, larger fuel tanks, repositioned elevators, and installation of Terrier missile launchers. In total, 3 Kitty Hawk class carriers were built, with the 4th one, USS John F. Kennedy, being considered as a subclass due to many minor design changes. JFK was originally supposed to be a nuclear-powered carrier, but due to budget cuts, was converted to be a conventionally powered carrier, and she was the last conventionally powered aircraft carrier built for the US Navy. You may be wondering why we haven't talked about catapults yet. Well, the reason is that prior to World War II, they were seldomly used. Even by the end of the war, it was estimated that about 40% of the aircraft launches relied on catapult. But in the early 50s, with the rise of supercarriers and jet aircraft, catapults became essential. After the war, Commander C.C. Mitchell of the Royal Navy developed a steam-based catapult system which was both effective and efficient in launching jet planes. The United States Navy was very impressed with this British invention and immediately bought 5 steam catapults. One was used for testing in Philadelphia Navy Yard. USS Hancock and USS Ticonderoga also got 2 catapults each. And then Project Steam was born, during which sea evaluations of these new catapults were conducted. A variety of jet aircraft were tested with these new steam catapults. Propeller airplanes were tested as well. Overall, the trials were extremely successful. The most significant attribute of steam catapults was consistent acceleration for most of its stroke. After the end of Project Steam, the US Navy adopted steam catapults on all of its carriers. An interesting tidbit is the 2 extensions at the end of the forward catapults, which were called the bridle catcher. The bridle would link the shuttle to the aircraft and would pull it down the catapult's track at increasing speed. At the end of the catapult track, the aircraft would depart into the air and the bridle would be flung out into the sea, unless the carrier had a bridle catcher, which would recover the bridle so it could be used again. But modern carriers do not use bridle catchers anymore, as bridles are now obsolete. Instead, the catapult launch bar is directly attached to the nose gear of the aircraft. During the early days of naval aviation, pilots relied entirely on their visual perception of the landing area as well as the aid of landing signal officers, or LSO. LSOs utilized colored flags, cloth paddles, and lighted wands. While LSOs are still used today in the US Navy, an optical landing system does most of the bulwark. Originally developed by the British after World War II, Optical Landing Systems, or OLS, was deployed on American carriers in 1955, which greatly improved safety on the flight deck. The original optical landing systems relied on a concave mirror that was gyroscopically controlled on the port side of the flight deck. But the next generation of OLS, which are also referred to as the lens, consists of a row of green lights called datum lights and a column of vertical lights. An amber light, called the meatball, travels up and down the column depending on the relative position of the aircraft to the flight deck. If the meatball is above the green lights, the aircraft angle of approach is too high. If the amber light is below the green lights, the aircraft is too low. And if the meatball is in line with the datum line, the aircraft is on the right track. At any given point, the LSO is in control of the lens and also in contact with the pilot via radio. The LSO would also operate wave-off lights, which are red flashing lamps that instruct the pilot to go full power or go around. The original idea was that the OLS would completely eliminate the need for landing signal officers. But when the OLS was introduced, the accident rate actually went up. Prior to using the lens, the accident rate on American aircraft carriers was 35 per 10,000 landings. After the introduction of the lens without the LSO, it went up significantly. But when the lens was combined with the LSO, the accident rate dropped to 7 per 10,000 landings in 1957. Sometimes technology or personnel alone are not sufficient for a better outcome, but combining the two was truly a great leap forward towards safer flight operations on the carriers, which is still in use to this day. The first nuclear-powered aircraft carrier took 3 years to build at a cost of $4.16 billion. USS Enterprise, also known as Big E, had 8 A2W nuclear reactors, each replacing one of the conventional boilers. Being nuclear-powered meant that USS Enterprise could cruise around the world for 20 years before needing refueling. Simultaneously, the U.S. Navy was building smaller nuclear surface combatants such as USS Bainbridge and USS Long Beach, as it was envisioned at the time that the future of American Navy was nuclear. But cost overruns prevented this from happening, as Big E was the only one built out of the 6 carriers originally planned. With a displacement of 93,000 tons, she was quite something, the longest naval vessel ever built. Big E had 4 rudders, which was 2 more than any other carrier, and she had the most amount of electronics installed on her at the time. That included 1,800 telephones for a crew of 6,000. The unique square-shaped island was the result of the most powerful radar system installed at the time. The ScanFar radar was a long-range air search and target acquisition radar which relied on vacuum tubes and consumed a lot of power. As you can imagine, it took a lot of space inside the island. ScanFar was one of the earliest phased array radars, a worthy predecessor to the future AN Spy-1 radar that is used in the modern Aegis combat system. The flight deck is a dangerous place to be as there are a lot of things that can go wrong. The following 2 accidents are prime examples of how the US Navy learned about how simple flight deck operations can result in huge loss of life. In 1969, USS Enterprise was almost lost due to a single rocket. An MD-3A Huffer, a tractor-mounted unit used to start aircraft, had its exhaust positioned 2 feet away from a Zuni rocket attached under the wing of an F-4 Phantom bomber. The exhaust heated the rocket in excess of 320 degrees Fahrenheit, which caused the rocket to explode. The blast damaged the Phantom's fuel tank, from which burning jet fuel poured onto the deck that set off a chain reaction with more planes and bombs exploding. Nearby USS Bainbridge and USS Rogers rushed to help. It took 4 hours to extinguish the fire. Sadly, 28 sailors lost their lives and over 300 were injured. 15 aircraft were destroyed and the flight deck took some major damage. 2 years earlier, in 1967, a similar accident happened aboard USS Forrestal. A Zuni rocket was missing a safety pin, and during the switch from external to internal power, an electrical power surge occurred, which caused the rocket to fire into the external fuel tank of an A-4 Skyhawk. The resulting fire from the spilled jet fuel started a series of explosions that killed 134 sailors and injured 161. The USS Enterprise and Forrestal fires prompted the Navy to revise its operational procedures, such as better weapon handling, improved firefighting, better communication between key senior personnel, and educating the flight deck crew on subjects such as ordnance cook-off temperatures and times. The 10 Nimitz-class carriers are the workhorses of American naval aviation. The carriers can operate over 7 types of aircraft and carry up to a maximum of 90. During flight operations, on a flight deck the size of 5 football fields, a carefully choreographed team ensures both safety and efficiency while traveling at speeds in excess of 30 knots. As many as 4 aircraft can be launched every minute, while simultaneously recovering aircraft. 4 elevators, each the size of 2 average city lots, bring the jets to the flight deck from hangars below. The various functions of the flight deck personnel are identified by various colors they wear. Purple for fuel handlers, yellow for officers and aircraft directors who are responsible for movements on the deck, green for catapult and arresting gear crew, blue for tractor drivers and elevator operators, brown for plane captains that ensure aircraft is safe to fly and inspected after landing, white for landing signal officers, safety observers and medical personnel, and finally red for crash and salvage teams and the ordnance handlers. The design of the Nimitz-class carriers is based on the lessons learned from Forrestal and Enterprise supercarriers. The ship's layout is somewhat similar to the Kitty Hawk class. The biggest design change from Enterprise was using 2 A4W nuclear reactors instead of 8. This greatly freed up space, which allowed Nimitz-class carriers to carry an additional 3 million gallons of fuel for aircraft on board and escorts. The 2 nuclear reactors produce enough electricity to power a city of 100,000. The carriers have about 90 days worth of food and supplies on board. 4 water distilling units provide 400,000 gallons of fresh water each day that are used by propulsion plants, catapults, and the crew. Flight deck angle was slightly reduced to 9 degrees, which improved airflow around the carrier. Defensive armament varies from ship to ship, but usually includes 3 or 4 Phalanx Sea-Wiz, a dozen or 2 Sea Sparrow missiles, and sometimes RIM-116 rolling airframe missiles. Starting with USS Carl Vinson, the ships have been constructed with anti-submarine capabilities. Starting with Theodore Roosevelt, the carriers were manufactured with modular construction, meaning that instead of building the carrier from the ground up, they were pieced together from prefabricated blocks, which greatly increased construction efficiency. The average cost of building each Nimitz-class carrier was $9.7 billion. Since the first Nimitz-class carrier was laid down in 1968 and the last one was commissioned in 2009, there have been quite a few changes as the class design has evolved. For instance, the newest Nimitz-class carriers, USS Ronald Reagan and USS George H.W. Bush, only have 3 arrestor wires compared to 4 on the previous ships. This was due to the introduction of the improved Fresnel optical landing system. During refueling and complex overhaul, which happens every 20 years, Nimitz-class carriers are updated with the newest equipment, which brings older carriers up to the new standards. At this point, Nimitz-class carriers have a mature design, with not many things that can be significantly improved. Class carriers suffer from chronic overloading of their electrical generators, but that's because the Nimitz-class was designed in the 1960s, when onboard technologies required much less electrical power. So now, it has a limited margin available to meet the increasing demand of electricity. In fact, the limited electricity supply of Nimitz-class carriers is the primary roadblock to installing new but power-hungry technologies. With this in mind, during the design phase of Ford-class carriers, the decision was made to future-proof the class from this problem by doubling the supply of electricity. Currently, only half of the electric power generation capacity is being used, with the remaining half available for future technologies. The U.S. Navy expects the Ford-class carriers to be in service for 90 years.
90 years is shortened from 250. When I was working with the program, they envisioned the last carrier going out of service 250 years after the first carrier started service. So they have shortened that. Mr. Test and I were talking last period on the break about energy consumption, right? The Navy's going to railguns, which are using electromagnetics to launch projectiles into directed energy weapons, lasers. Offensive laser weapons can't go on small ships because they don't have enough power to run a laser. So that's why a carrier like this might have so much electrical generation capabilities to put a laser on it in the future. That might be one of the things they're considering. So as they said in the clip, the Nimitz class has reached the end of what it can do. It's based upon design, right? They can't make the reactors more powerful, and it doesn't make sense to upgrade them because the hulls are old. They don't go for more than 50 years. So the Ford class, previously CVN 21, had some goals to achieve. So increased sortie rate, increased operational availability, future-proofing, which we talked about, and then decreased acquisition and life cycle costs. But paramount to all of that is ship survivability. As you saw during World War II, the armored aircraft carriers didn't sink, the unarmored ones sank. The Navy learned we want ships to be able to survive a battle, so survivability is big. They want the ship to be able to make it home. So they decided to use a Nimitz class hull, but made changes in the design and used new technologies. So from about the hangar bay below that, it's still a Nimitz class hull, but above that was redesigned, and a lot of the new technology went up above the hangar bay. So another goal was to eliminate sailors, right, through automation and decreased mechanical systems, right? So sailors are expensive. Back in 2005, the average sailor cost the taxpayer about $150,000 a year. So if you times that by 500, you could save $75 million a year per aircraft carrier in personnel costs. Times 50 years, the expected life of the carrier, you'd save $3,750 million in personnel costs just by eliminating 500 sailors. They haven't been able to achieve that number yet. They're down about down 200 sailors, so they got a ways to go. I'm going to just talk about some of, not all of, the improvements they made. So advance the resting gear. The wires that the tail hooks catch are still on the Nimitz class stopped with hydraulics. It's hard to control the amount of force that's used. That it puts a lot of stress on the plane when it starts pulling on that wire. Stress on the aircraft reduce the life of the aircraft. So we went to stopping the cables with electromagnetics. The force can be applied more gradually, and we can control it with software. We can't do that with hydraulics. So not only is the system lighter, right, reducing the weight of the ship, which is a good thing, it can also recover all of today's aircraft and future aircraft. As planes get heavier, right, you've got to adjust the needs to stop it. But also UAVs, unmanned aircraft, they're not built to land on aircraft carriers. So if a UAV tried to land and catch that wire, there'd be too much stress on it. It would not be good for the unmanned aircraft. But with the advanced arresting gear, that is capable. Advanced weapons elevators, so the ones on the Nimitz still use cables to pull the elevator up and down. The new one uses electromagnetics, and that greatly reduces the maintenance for the cables on the elevator. So with reduced maintenance comes reduced manning requirements. Dual band radar, right? So now the radar is, it's not spinning, it's arrays on the side of the ship that just shoot out energy. They don't spin anymore. So that system replaced up to 10 spinning radars. And the new radar, it's more powerful, and because it's an array, you can focus it in one area down to a pinpoint if you need with software. But it does long-range search, and it searches from the horizon up into the sky and can track several objects at once. This is the same technology used on the guided missile destroyers and the cruisers. That's known as the Aegis radar system. And a cruiser can track over 300 airplanes at once with their radar and engage them. The computer will prioritize what planes need to be shot down first, and then just launch missiles at them. But it is a very impressive system. I've seen it used out in the sea. Electromagnetic launch system, right, that's the steam catapults. We've replaced steam with electromagnetics. Steam has reached the capacity of what it can launch. Aircraft keep getting heavier and heavier and heavier, but steam hasn't produced more power. So right now we're at the limit of what we can launch for a fueled and armed fighter plane off the deck of a carrier. emails will allow more weight to be shot off the carrier and also produces less stress. When they launch the steam catapult, again, it puts stress on the airframe and reduces the life of that plane. So today, a fighter might cost $100 million or more, so we don't want to shorten the life of it by putting undue stress on the airframe. Joint Precision Approach and Landing System, that is a new radar system on the back of the ship used just to aid aircraft landing on the ship. So there'll still be the LSO, there'll still be the meatball that they have to watch, but now there's a radar system that will aid them in landing on the ship. And then lastly, what makes this all possible are new reactors, right? So the 2 reactors on the Ford class, each reactor is 300 megawatts. The ones on the Nimitz were only 100 megawatts. So not only do they have more power, but we don't have to produce as much steam. So instead of using the energy to produce steam, we can make up to 3 times the amount of electricity on the Ford class. And they've got a significant weight reduction, right? So the new design eliminated 1,350 tons of weight. That's a lot of weight to just disappear. So this is the first carrier in the class, the Ford, and without any planes here, it's easy to see. Here are the new weapons elevators, right? So the island is smaller and moved back. On a Nimitz class, the island is built like this, and this plane elevator is back here. So what this has allowed is more deck space for aircraft. So the new process to arm and fuel planes is to line them up along this side of the ship and fuel them and arm them while they're parked here, and then they proceed to their catapults to be launched. On a Nimitz class carrier, your plane can be parked anywhere, here, here, back here, and if it needs to be armed and fueled, they bring the weapons and the fuel to the plane. Now they're bringing the plane to the weapons and the fuel. It should speed up the process, allowing more planes to be launched than in the past. Here are some pictures of the new island. So here you can see the phased array radar panels. There's one here. Same thing facing forward, and there's one on the other side. They cover 360 degrees around the ship. There's no more spinning radar. This is the new radar, right? So that's the future. So we're out of time, so if you guys have any questions, let Mr. Testa know. He can send them to me and I can get a response. And if you guys are interested in doing more of this, I'm more than willing to come back at some point in the future and we can explore something in greater depth. Thank you guys very much. Have a good weekend.
Appreciate it. All right, guys.